Yeah, welcome to the Stats Jungle, where tonight's topic is all about z-scores. And so basically, we're going to do a quick intro here, and it's very, very similar to the normal distribution we did yesterday. This is basically what yesterday looked like, and we're going to try to standardize that and create a bell-shaped curve that looks like this. Basically, we're saying Every curve we did yesterday had different numbers along the bottom because it depended on what the mean was and then the standard deviations off of there. So here you'll see that 1010 was the mean, and it looks like 20 is the standard deviation because it was a 20-point jump to every number. Well, we're going to try to standardize that so we can compare apples to bananas and so forth. And so here we go. A z-score of 0 corresponds to the mean. A z-score of +1 is one standard deviation above the mean, etc., etc. Here's what I thought was a really neat scenario and question to kind of get our thinking in the right frame of mind for tonight. It says, suppose you took both a math test and a Spanish test on the same day, and the average score for both of them was an 80. Well, you got an 86 on your math test and a 90 on your Spanish test. So I think right there, the assumption that we typically make is that you did a lot better in Spanish than you did than your math test that day. However, relative to your fellow classmates or your fellow students, did you necessarily do better in Spanish? And here's what we're going to try to say. For instance, let's talk about math. What if, hypothetically, what if you found out the next day that the standard deviation was 4? Okay, that means your score of 86, which was 6 points higher than the mean, was actually 1.5 standard deviations above the mean. Okay, in Spanish, let's say that same next day you found out that the standard deviation on that test was a 6, or I'm sorry, was an 8. So your score of 90, which was 10 points higher than the mean, was only 1.25 standard deviations above the mean. Okay, so what you found out, because the standard deviation in math was a little bit lower, what they're saying is a heavier percentage of the population within your class was really closely clustered around 80. So by getting an 86, you kind of separated yourself and with a greater distinction than you did in Spanish. And so relative to your classmates, we'd say you actually did better on the math test because you outperformed or outscored a higher percentage of your classmates. Here's a couple different distributions that I wanted to look at before we went any further here today. We could have introduced them in the last video. Either one, it'll work out about the same. So really what we've introduced you to so far is what we call normal distribution, but there's other types of distributions, and I didn't want you to think that normal was the only type. So we're going to introduce you to first what's called skewed left. And we say that this is skewed left because where's the long tail? There's a long tail here on the left side of the graph, so we say the data is skewed left. Or the opposite of that would be skewed right. And so it's skewed to the right because of what? There's a long tail on the, whoops, that should say, that's a typo right there. That should say on the right side of the graph. So right along here is that long tail we're seeing. So we've got skewed left, we've got skewed right, and then we'll compare that to the one that we spent all of our time on so far. We would say that this diagram here is approximately normal. Approximately normal. We didn't say exactly normal. It's just approximately means it's very close to being normal. Very, very close. All right? Because the distribution is symmetric with a what we call a single peak. All right, and is bell-shaped or mound-shaped. So as we indicated in the opening slide, today's theme is all about being able to standardize this bell-shaped curve, this normal distribution. And we're going to say that a z-score indicates how many standard deviations, that's what it's all about, how many standard deviations an element is from the mean. How many standard deviations an element is from the mean. So let's look at a bunch of different examples. If you said we had a z-score equal to 0, that represents an element that is exactly equal to the mean. So what I like to do right there is let's go ahead and say that 0 right there is the mean. And that's going to be true 100% of the time when we're working with normal distribution. Now, if a z-score was greater than 0, that represents an element that is greater than the mean, or we could say above. we can say greater than, or we could say above. So on this diagram, you'll see +1, +2, +3. All of these z-scores are greater than 0. And basically, so any data element that falls on this side of the graph is said to have had a positive z-score, and that data element is above the mean. Now compare that to this next one, which I think is just the opposite. If we said we have a z-score that's less than 0, well, that represents an element that is less than the mean, or we could just say below the mean. You know, so here's -1, here's -2, here's -3. Those are all z-scores less than 0. So any data element that falls on this side of the mean is said to be below the mean. Number 4, a z-score that's equal to 2 represents an element that is exactly 2 standard deviations above the mean. And I knew it was going to be above because this 2 here was a +2. So we're looking right here, that data element would fall right there at +2. Let's see. A z-score of -1 represents an element that is exactly 1 standard deviation below the mean. Again, the negative corresponds to below. So we'd be sitting right here within the distribution, right here at -1. All right, we're going to do a little bit of extra writing here on this one, but just to be crystal clear, we said this letter Z, and this is automatic. As soon as you see the letter Z anytime in the study of statistics, we're going to say it represents a variable that has a standardized, normal distribution. Not just a normal distribution, but a standardized normal distribution where the mean is 0, automatic, and the standard deviation is 1 unit every time. So what we're basically saying is that we're always going to put a 0 here, and it's always going to be +1, +2, +3. Hence, it's standardized because it's going to be that way every single time. So we've got a quick little formula to calculate a z-score because we're just trying to convert every score back to the standardized element. It may look a little goofy at first, but I think overall, with a little bit of practice, you're going to find that it's one of the easier ones we do all year. Basically, we're going to take the value that you started with, whether it's a score or a measurement of some sort, and you're going to subtract the mean from it, and then you're going to divide it by the standard deviation. Symbolically, what that might look like, I usually cross my Z's so that they don't look like 2's, is we're going to take a given score, you're going to subtract the mean, and then divide by a standard deviation. So whichever formula you prefer, whichever one makes more sense to you. Now conceptually, one of the big ideas throughout the video tonight is that the area underneath the curve is equal, and I really want to stress this word, equal, to the probability of that event in that region occurring. So let's say we've got the z-score right here. The area underneath the normal distribution curve corresponds to the probability of it possibly happening. So in other words, what we're saying is the area of the entire normal curve is equal to 1. Okay, that's if we shaded everything in. The area would be 1. So this little region over here on this side is some number less than 1. In fact, we could even say it's definitely less than 50% because 50% would be right here. So maybe it's around 0.25. Another example really quick is here we've shaded everything above the z-score or to the right of the z-score, and the area is 0.1075. So we would then say the corresponding probability is 10.75%. Or because we said everything has to add up to 1, if I subtracted that number from 1, that would tell me the area of everything on the other side of the graph here. So the probability that it falls in this section is 89.25%. Last little picture here. So again, here's our formula. They used a little different symbol for the mean, which we may see from time to time. This is a Greek letter mu, but that's the same thing as our x bar. And so here's, we've got a z-score of 0, a z-score of 1. We shaded everything in between. We got an area of 0.3415, which is equivalent to 34.13% for a probability. All right, here's our first real live question of the day. And they want me to find the area underneath the normal curve between a z-score of -1 and a z-score of +2. And so our big theme here is going to be identifying the two z-scores and then trying to shade in the appropriate region. So I've identified -1, and then here's a z-score of +2. And I want to identify the area between those two vertical lines. And so I'm going to shade in all of this region here. And I want to try to find the area. Now, we're going to use our calculators hardcore from this point out. And so I'm going to try to describe some of the buttons I'm hitting, and then when I'm all done, I'm going to show you a picture of what my screen looks like just to confirm that yours is looking the same and that you're able to follow along. So we want to go to what's called the distribution menu. And so you might want to take a second to try to hunt around for that. But it's very just to the left of your clear button. And it is the blue letters above vars. And so my first step is to hit second and then distribution, which is abbreviated DISTR. Now once you get to that menu, we are looking for option number 2 on that menu, which says normal CDF. DF, just like that, and it shows an opening parenthesis with it. And so once you choose option number 2, it's going to take us back to the home screen. You may or may not have a stat wizard. Either way, I think the stat wizard makes it more self-explanatory. And so we're going to go normal CDF. And let's see, there's 4 things we're going to type in. We're going to do -1 for the low z-score. We're going to do +2 for the high z-score. We're going to do a 0 for our mean, and we're going to do a 1 for the standard deviation. And then you should be able to hit enter. And when you hit enter, you'll get 0.81859,467, etc., etc. Okay? And what that does is that corresponds to the area of that particular region, or we could say that there's an 81.859% chance that a score would fall between a z-score of -1 and +2. So we could either do area or we could do probability, either one there that you congruent basically. Now to try to generalize what you're doing on your calculator, so once you do normal CDF, your calculator is always expecting 4 arguments. The first of those 4 arguments is your lower z-score. Okay. The second argument is your higher z-score. So you got your lower bound, you've got your upper bound, and then you're always going to put in your mean. And then the fourth and final argument is going to be your standard deviation. Now ironically for us today, because we're using a standardized normal curve, your mean's always going to be 0 and your standard deviation is always going to be a 1. So the only thing that's ever really going to change from problem to problem today are these 2 scores right here. Okay, a little more practice with the calculator. We want to find the area underneath the curve between a z-score of -2.451, and I'm going to kind of estimate where that is. It's not the most easy decimal to plot here. And then a z-score of 0.891, which would be just shy of +1 in this area right here. So I'm going to shade in everything in that region, and then I'm going to try to find the area of that curve by using my normal CDF. So I'll say area equals, and on my calculator, really doing basically nothing by hand today, I'm going to enter in my, whoops, that's a 0.451, my low z-score, and then my higher z-score, and then our mean and our standard deviation. Like we said, those last 2 numbers won't change. We're going to go ahead and hit enter, and depending on how many decimals, I'm going to go 3 decimals. So what's 0.80668 on my calculator, I'm going to go 807 for 3 decimals, which would then be converted to about 80.7% chance that the score falls within this interval right here. This one's got a slight twist to it. Instead of finding the area between 2 z-scores, they just want me to find the area that's to the right or above a z-score of 1.5. So my 1.5 falls there. To the right of that would be everything on this tail end. Now theoretically, this normal curve extends all the way to infinity. Although basically by the time you get to a z-score of 4, the normal curve's almost virtually touching the x-axis, although it's not technically. And so you can only imagine by the time you get to 5, 6, and 7 how much closer it is there. So here's what we're going to do. We're basically going from a z-score of 1.5 all the way to infinity. Now, as far as our calculator goes for this normal CDF, what we're going to use as a routine is just we're going to use 999, and we're going to say that's going to be close enough to infinity to give us an accurate answer. So I'm going to go normal CDF. My lower score is a 1.5, and my high score is infinity, but we said that's going to be 999. Well, then we've got a mean of 0 and a standard deviation of 1. Now, as you're typing it in the calculator, it's always a good time to kind of create a prediction. And I guess, first of all, were you expecting or predicting an answer bigger than 50% or smaller than 50%? And I was predicting something significantly smaller than 50% just because the area visually looks so much smaller here. And I got again, if I go 3 decimals, it would be 0.067. Which gives me a probability of 6.7%, so that is a very small number. Remember this, 50% would be everything from here over, and so we're using a lot less space than that this time, so I think it makes sense to get such a small percentage. Okay, a little similar to the last one, except this one we want all the area to the left of a particular z-score, and this is a positive 0.43, so that's going to put me, let's see, I think in this neighborhood right here, maybe over a little bit more than what I drew. And again, we're just kind of estimating for shading purposes. We want all the area to the left of that. Now what you'll notice is the region that I'm shading in is more than 50% of the graph. So the wheels are turning and I'm expecting an answer that's bigger than 50%. Not a ton, but maybe around, somewhere between 60 and 70% is what I'm predicting. Now what we're doing is we're going to go from a z-score of 0.43 and extend all the way, theoretically, to negative infinity because we're saying this normal curve continues on forever. And we're going to use negative 999 as a safe bet. So we're basically saying negative 999 standard deviations below the mean. And that's really a crazy number to think of. When I get ready to go type my normal CDF into the calculator, I just want to be careful. The smaller of the two z-scores has got to go first, and this negative 999 is the smaller of the two scores, comma, and then 0.43 is the bigger of the two scores, then our mean and our standard deviation, and we'll go ahead and hit enter. And I got to 3 decimals, the area is 0.666 or 66.6% probability. Now that we're comfortable shading in the appropriate regions and understanding that the area and probability are the same number today, and we're pretty good with the calculator, I would say, we're going to try to apply it to a real live example. And so here we go. Let's say that the cost of a new laptop, all the costs are approximately normally distributed, and there's a mean of 650. And there's a standard deviation of 125. Now, what I want to do is I want to try to standardize these two amounts right here. What is the probability that a new laptop costs somewhere between $500 and $700? So let's try to standardize. We'll start off with the lower number first. So our lower z-score, if we go back to that formula we introduced you to a few minutes ago, I'm going to start with 500. I'm going to take 500. I'm going to subtract the mean, and after I subtract off the mean, I'm going to divide by 125, which is our standard deviation. And that makes my lower z-score negative 1.2, which again means 1.2 standard deviations below the mean. Now my upper z-score, I'm going to take the $700, and the first thing I do with my 700 is, again, subtract off your mean and then divide by your standard deviation. So I got 50 divided by 125, which turned out to be 0.4. So these are my two z-scores, and I want to shade in the particular region. So negative 1.2 would put me in this neighborhood. And so negative 1.2, that represents a laptop that costs $500. And then a z-score of 0.4 puts me in this neighborhood right here, 0.4, which corresponds to a laptop that costs $700. And so I want to shade in this region. I want to find all the area underneath the curve, and that'll tell me the probability that a new laptop is going to fall within that range. So I'm thinking normal CDF. We're going to get really good at hitting second distribution or second vars. We've got our lower z-score, and then we've got our upper z-score. Our mean is always 0, and our standard deviation is always 1. And so the area underneath the curve was, let's see, about 0.540, which translates to a percentage of 54% chance that a new laptop costs between $500 and $700. Okay, we'll stick with the same data here, and as far as the laptops go, and now we want to figure out what's the probability that a new laptop costs more than $800. So what I want to do is I want to find the corresponding z-score for a laptop that costs $800. So the first thing we're going to do is we're going to take that $800 and we're going to subtract off the mean, minus 650. And then once we subtract off the mean, we're going to divide by the standard deviation. And let's see what z-score that gives me. So I ended up with a z-score of 1.2. So if I plotted that, that's going to put me in this ballpark right here. And we want to go above $800 or above a z-score of 1.2. So I'm shading in everything here. Remember, we do extend towards infinity. So I'm going to go from a lower z-score of 1.2 all the way to an upper z-score of 999 is our safe bet. Ironically, if you used, I bet you could test this, if you used an upper z-score of 50 instead of 999, I bet you'd still get a really good answer. But we just know that 999 is a really safe bet. Of course, if you used a number even higher than 999, it'd be even that much safer. Low score, comma, higher score, 0, 1, hit enter. And I got an area underneath the curve of 0.115, which translates to a probability of 11.5% chance that a new laptop's going to cost more than $800. All right, one more laptop question. And I think this is a great chance to hit the pause button, test out how comfortable you're feeling with these z-scores and finding these probabilities, and try solving this one on your own. Now we want to find the probability that a laptop costs less than $675. So I'm going to say the z-score that corresponds to $675 is going to be 675 minus the mean of 650 divided by the standard deviation of 125. And let's see what that turns out to be. That gives me a z-score of 0.2. Now that is a positive 0.2. So that's going to slot me in here just to the right of the 0 because it was a positive 0.2. And I'm going to shade everything into the left because we want to know we're focusing on ones that cost less than $675. So kind of the wheels are turning in the back of my mind, and I'm expecting an answer that's a little bit bigger than 50% because we've got just a smidge over half of the curve is shaded in. Now, as far as finding that probability, remember, we're going from 0.2 and we're extending all the way to negative infinity, which is negative 999 for us. And if I type that in, let's see, I'll go right here. Normal CDF, the lower z-score of negative 999, the upper z-score of 0.2, mean, standard deviation. And when I hit enter, I got an area of 0.79, which translates to a probability of 57.9% chance that a new laptop costs less than $675. All right, we're going to change the context of our question just a little bit here for the next few examples, and suppose that the number of fluid ounces in a bottle of Pepsi is approximately normally distributed with a mean of 12 fluid ounces and a standard deviation of 0.4 fluid ounces. Now here's the kicker. What's the probability that a randomly selected bottle of Pepsi contains somewhere between 11.3 and 12.3 fluid ounces? Now here's the best part of tonight. I don't know if you noticed, but yesterday I wouldn't say that we were faking the numbers, but I had to be really careful about what numbers I picked in that normal distribution, because the chart we were using, we could only go either with 1 standard deviation or 1.5 or 2 or 2.5, or it had to be like a really nice packaged number. Today, that the same concern does not hold true. We could really get as realistic as we possibly want. And so let's get our upper z, or no, we'll start with our lower z-score. And again, same formula. We're going to take the 11.3, we're going to subtract the mean, divide by my standard deviation, and it's negative 1.75. Why is it negative? Well, that's because 11.3 falls below or to the left of the mean. What's my upper z-score? All right, let's see what we got cooking here. Now, this number, the 12.3, is above the mean. So when I do 12.3 minus 12, I'm going to get a positive number divided by the standard deviation, and I got a positive 0.75. So let's shade in the corresponding part of our graph so we can visually, geometrically see what's going on here. Negative 1.75 puts us in this neighborhood, and positive 0.75 lands us there. We're going to shade in everything in between. Looks like a good chunk of space, so we're expecting a relatively large percentage of the Pepsis that will fall in between these fluid ounces. We're going to go normal CDF. In other words, second VARs or second distribution on the calculator. We're going to enter our low score first, followed by our high score or upper score, 0, 1. Final answer, area under the curve is 0.733, translates to a percentage of 73.3%. And again, I think that fits because, again, that corresponds to the amount of area we've shaded. Well, I tell you what, we've got 2 more quick examples, and if you're feeling really confident, don't be afraid to try these on your own and buzz right through them here. But if you're feeling shaky, then by golly, that's what these next 2 examples are for, to just kind of build a little confidence before we break for the night. And we want to know what's the probability that a randomly selected bottle of Pepsi contains more than 11.5. So let's find his z-score. So we're going to take 11.5, we're going to subtract the mean and divide by the standard deviation. And we are expecting a negative number because 11.5 falls below the mean. And I got negative 1.25 for my z-score. Let's see, graphically, that's going to put me in this ballpark, and we're going to shade everything above it. And look at this, we are shading in just a huge chunk of the curve here. Got a lot of area we're going after. So we're expecting a very large number, one that's significantly higher than 50%. And remember, so we're going from negative 125 all the way to infinity, and that's where we'll use our 999. And so my normal CDF, I'm going to start with my lower score, followed by my upper z-score, 0, 1, and that gives me 0.894 for the area, 89.4% chance that a bottle of Pepsi contains more than 11.5 fluid ounces. Last one for the night. We want to find the probability that a randomly selected bottle of Pepsi contains less than 11.1. So my z-score, 11.1 minus 12 divided by the standard deviation, has us sitting at a z-score of negative 2.25. Graphically, that's going to put us in this neighborhood right here. We're going less than or everything to the left of that. Look at that little squirt. Just a very small region. So we're expecting a very small percentage, one that's significantly less than 50%. And so we're going from a z-score of negative 2.5 all the way left towards negative infinity. And when we say negative infinity, we're thinking negative 999 is my lower z-score. So our normal CDF is going to go negative 999, followed by negative 2.25, followed by 0, followed by 1. We hit enter. We got an area of 0.012, or 1.2% of a 1.2% chance that a randomly selected bottle of Pepsi contains 11.1. So if you fell into that range, you know you were having a bad luck day, and that's you got gypped on that bottle. But hopefully it'll even out, and the next one you get will have a lot more than that. So anyway, have a great night. We'll catch you tomorrow.